So the first question is, what type of triangle is this? When students look at this right away, they usually think it's equilateral, which is where all three sides are the same length. But what we're going to be doing in geometry is we got to prove it. So instead of saying, like, take my word for it, all three sides are the same length, or no, I don't think that all three sides are the same length, we're going to figure out, how do you know? So there's got to be some type of math involved. How can we tell the length or the distance of a side? So we're going to make this little triangle and we're going to use the Pythagorean theorem. So there's this little right triangle right here. And there's one space up and 4 spaces over. So if we do the Pythagorean theorem for AB, a squared plus b squared equals c squared. 1 squared plus 4 squared equals c squared.
Okay, I did it.
And together I'm getting about 17. And let's just leave it radical 17 for right now. If something else is also radical 17, then we know it matches. So if I look at the other sides here, I can get another 1 and 4 right over here. On this triangle, there's 4 spaces down, 1 space over. So that side is also going to be radical 17. I'm going to just put like a little annotation over here, maybe BC is equal to AB, and they're both equal to radical 17. And then this other one, AC, making a right triangle with it, but I'm getting 3 and 3 for this one. So AC, 3 squared and 3 squared equals c squared. 9 and 9 makes 18. And we square root both sides. So what type of triangle has 2 sides the same? These two both work out to radical 17, but this side works out to radical 18. So 2 sides the same is an isosceles triangle, and that's what we're going to kind of focus on for this rest of this unit. So I went ahead and graphed this isosceles triangle below. Feel free to pause the movie to be able to graph it yourself. My goal is to try to make short videos, but you feel free to pause them if you need to, rewind, fast forward, whatever you need. So I plotted A, B, C. I also made some segments there for A, B, C. I know in the directions it says isosceles triangles, so that's exactly what it's going to be, but we're going to be proving it and kind of showing the math that goes with it. So same thing what we were doing before is that we're going to make these right triangles. So connecting A and B, we want to go straight up from B, straight over from A until they meet at this right angle over here. And if we know 2 sides of a right triangle, we can find the third by the Pythagorean theorem. So we count the spaces if we go horizontal, and we count the spaces that go vertical, and then we can use the Pythagorean theorem. I don't care if you write it every single time or if you don't. I'm trying to do good modeling, so I'm writing it a lot. And I'm going to end up with radical 20 for the distance for AB.
It always starts.
So next up I'm going to do BC. Now notice BC, we can't make a line, a right triangle out of it. And the reason being is it is only horizontal. You don't have to show any work. You just count 4 spaces and put 4 in the chart. So there is no work that, you don't need to make up work for something where it's not really necessary. That is just a horizontal line. And when we look at AC, it's diagonal. So we do need to do this straight up, straight over, make that right angle. 2 and 4 in the Pythagorean theorem. And I kind of have a hint as to what it's going to be from looking up here. So I'm going to kind of cheat a little and put 4 and 16. And I know it's going to work out to radical 20. So the idea of doing this distance is for you to see, it doesn't really matter what radical 20 is. You could reduce it. I think it works out to 2 radical 5. But the idea would be to see that AB and AC are congruent to each other. That's kind of the big idea. And I'm going to actually put that right down here. Properties of isosceles triangles is it has 2 sides congruent. Now I'm going to have you do a bunch of these papers with lots of different shapes. So we will find more things out along the way about other shapes if we do the slopes of the sides and things like that. We all are supposed to make a concluding sentence at the end where you put all your findings into one sentence as well. So if we're looking at the slopes, these little triangles kind of help us figure out the slopes as well. Slope of AB would mean how much rise and run to get from one point to the other. And we want to do it as we're seeing it. We start at the left, so we're actually coming across B first, and how much up and over to get to A. So 4 over 2. And if we reduce it, we would get 2. Same thing with B to C. How much up and over to get from B to C? We're going up nothing and over 4. If you type that in a calculator, it should spit out 0. A to C, from A, almost like down and over, we would be thinking of it's going down 4 and over 2, or negative 2 total. I have you do that even though it's not really telling us anything. We don't have negative reciprocals for perpendicular lines. We don't have congruent slopes, so that means we don't have parallel lines. But along the way, we're going to do this, and we will find out ones that have some things in common. The concluding sentence is we want to put the information that we found that's important in one sentence. The triangle is isosceles because sides AB and AC are equal length.